Okay, so the final group is going to talk about liquid-liquid separation. Baxton Sleeter, Josiah Gamble, A.R. Godsey, and Dakota Brown. Team, take it away.
Okay, I'm just going to give you a quick outline. First, we're going to talk about the concept of our project, which was liquid-liquid separation. We're going to talk about our specific system, not just in general. Show you the schematic of our apparatus and how we built it and everything. Our results, some obstacles we had, some safety issues, and a budget or some acknowledgments. And AR is going to talk a little bit about the concepts.
Alright, so the basic concept behind liquid-liquid equilibrium is that in two phases, if the total Gibbs free energy is lower than it is in one phase, it'll split into two for given temperature and pressure. So we have three criteria. We have mechanical equilibrium, thermal equilibrium, and chemical equilibrium. And that says that the pressure, temperature, and the chemical potential for a species is the same in all phases. The chemical potential states that the fugacity is equal, and from fugacity being equal, we get that the mole fraction times the fugacity in one phase for one of the species is equal to activity coefficient. Mole fraction times the activity coefficient for one phase is equal to the mole fraction times the activity coefficient in the second phase. And we've derived these equations here from algebra many times in class, and that basically says, well, I'm going to read it off, but you can see it there. And we can use solubility diagrams to help us predict our liquid-liquid equilibrium using external data. And at constant pressure, these are useful because some might have upper constellate solution temperatures and lower constellate solution temperatures, or in some cases even have both. An example of that is here. Here we have a closed loop with both an upper constellate solution temperature and lower, and we have just an upper constellate solution temperature here.
This is a diagram for R specifically, but it's the mixture of water and propylene glycol and propylene. As you can see here, we have just one liquid phase around room temperature, and then as you heat the solution up around 0.5 mass fraction, you'll have splitting into two different liquid phases. So here's our actual apparatus that we used. We used this box here. You can see is just a normal fish tank. We have a dividing wall here made out of plastic. We have a heater in there. What happens is then we fill one side up with our mixture, heat up to a temperature above the lower constellate temperature, then we'll have phase splitting and then a difference in density, and as you can see here, they'll eventually separate into two different sides of the container, one side being the water, the other side being the organic phase. Our actual procedure is we take our 40% by mass solution, put in the container and heat it up. At the different temperature, it's going to split into two different phases, and then the difference in densities between the water and the propylene glycol and propyl ether will result in two different layers. The more dense water is going to sink to the bottom, and then propylene glycol and propyl ether is going to come to the top. Then once they separate into two phases, we're going to initiate gravity flow from the container to make it a semi-continuous process, and as it flows in, it's going to separate. The organic phase is going to come off the top, and we're going to be left with water on the other side of the tank. So just a little bit more about our mixture. We have a lower constellate temperature here, as you can see, at 32 degrees centigrade. So at room temperature, they should be completely miscible in each other. And as we heat up, for our mass fraction of 40%, around 35 degrees C, they'll split into two phases, and we'll be able to separate the liquids. Now talk more is Preston.
This is our specific propylene glycol and propyl ether. This is the same slide that you saw earlier. Only we're going to 40%. You go up at 40% from room temperature, and then take it to around 40 degrees. You should get the phase separation. In one phase will be this phase over here will be rich in the glycol ether, and so we're predicting probably around 64% instead of 40%. So we're actually enriching the phase without distillation, just by phase separation. Here are our expectations, like I pointed out, using phase diagram. You get about 26% glycol ether in the water, what we're calling the water phase, and 65% in the organic phase. We attempted to actually measure the compositions of the phases. The numbers were a little inaccurate, we found out, and I'll present that next. Some of the obstacles that we faced. Systems will split at room temperature, and pressure close to standard conditions are not very common. They're common enough to be studied, but they are still not the norm. I would say most liquids will act like they're used to. Will just mix at room temperature. The chemicals that we use are very expensive. The bottle of propylene glycol per liter was $65, which is